So let's start. Thank you very much for coming to another seminar. Today we have Tian. She's a PhD student at the Global Change Group under the supervision of Vilarrasa. And well, she will be talking about her PhD project. So thank you very much, Tian, and the floor is yours.
Thanks. Thanks for coming here. And today my topic is the application of machine learning to reduce the subsurface uncertainty based on ground deformation measurements. And as just mentioned, this is part of my PhD work and under the guidance from my supervisor, Victor. And this topic will explore the machine learning applications to the large-scale carbon storage project. So what is the carbon capture and storage? The general idea is quite brief. We capture the CO2 from power stations or from industrial sources and compress the captured CO2 and transfer them by ship or by pipeline, and then store them permanently into the underground geological formations. And sometimes part of the CO2 can be also utilized in other industrial productions or even the energy projects. And this is a very useful tool because from a lot of reports, such as the reports from International Energy Agency, they have this sustainable development scenario, and we can see overall the CO2 emission reductions increases by time. And at the beginning, CCUS just take a very small part of the entire reduction, but by 2070, it can reach a very high amount of the CO2 emission reduction. And overall, by 2070, the CO2 emission reductions can reach about 40 gigaton CO2 per year. So this is a very large number. And so we believe CCS can be a very useful tool, but we still faces a lot of challenges. Because we want to save the CO2 safely and permanently. So in this study, we mainly focuses on the subsurface challenges of CCS. The subsurface conditions are always very complicated, and there are a lot of processes during and after the CO2 injection. And we summarize them into THMC coupled process. The T means the thermal. In this term, it means the heat transfer and temperature changes. And H means hydraulic process. It always means the fluid flow through the pores or fracture rocks. And I means mechanical process, and it is related to the stress or strain or even the deformation in the rock. And we focus on this because it's really important to analyze the subsurface, like rock stabilities or faulting system. And same as chemical, during the injection of CO2, there will be a lot of chemical reactions between the injected fluid to the surrounding rocks or fluid. And it can cause different reactions within the subsurface, and these processes also influence each other. So it's a very complicated system. And in our study, we mainly focus on the hydraulical and mechanical processes. So here is a very famous example of CCS project at In Salah in Algeria. This is a very early stage first CCS, and it was successfully because it injected 3.8 million tons of CO2 during the 3 years of injection. And our research idea is actually generated from this project, because when we capture CO2 and try to inject it into the deep ground, this depth is always deeper than 800 meters. And although the density of the CO2 is higher, but it's still lighter than the surrounding fluid. So because of the buoyancy, the CO2 goes up. Then we need some low permeable rock to cover the reservoir. So so we can prevent the CO2 leakage. And then also when we inject the CO2, the pore pressure of the formation increases, so the effective stress decreases, and this will cause the deformation. And when we do the model, we expect after the injection, we can have this expected deformation on the ground. But actually from this In Salah project, it shows a quite different deformation pattern. And we were thinking why this happened. And after the investigation, the researchers found there is a very large fault zone at depth. So here generated our research motivation, like we can actually investigate the subsurface structure by the ground deformation. And to start our study, we try to build a forward model at first and then do the backward and to say the inverse model, if the inverse model can predict the ground deformation or to predict the subsurface structure accurately. So here, as I mentioned, the forward model is actually built on this analytical solution, which came up by Wu in 2023. And it provides a closed form solution to calculate the ground deformation in two-dimensional. This plot is the geological model and is the model we are using in our research. And we can see this line, this black line is the fault, and these two blocks represents the reservoir. In our model, we only assume the fault to be normal. So it means the deep angle is between 0 to 90. And also we simplify the model. This fault has no thickness. So we can simplify this model. The fault can be the line, can be a straight line in our model. And in this equation, it has a lot of different parameters. And in this right circle, these parameters are from geomechanical. And we will use this analytical solution as the first step in our study. So here is the workflow. We first generate the data and then use this generated data set to do the feature analysis by correlation matrix, and also we did this principal component analysis. And then after this, we built two different models. Because we have a bunch of data, it's very huge amount. So we were thinking the artificial neural network can be a very useful tool to predict to do the prediction. And we also want to compare its performance with another model. So we selected different algorithms in classical machine learning approaches. And actually we have tried different algorithms like decision tree or random forest, but they don't have really good performance. So finally, we select this gradient boosting regressor as the algorithm for machine learning. And then we split our generated data into training and validation data, and we tune the hyperparameters. And the last step is to test our model. So we introduce an extra data set from another data source. This data is generated from numerical solution, and we test our model by this numerical solution data set, and then compare the model's performance by their accuracy and running speed. So first step was the dataset generation. As I just mentioned, this analytical solution has 9 different parameters, and each parameter has their own value ranges. So we need to take different value ranges of each parameter and put them into this analytical solution and calculate the corresponding ground deformation, and use this one, like loop the parameters one by one and calculate the ground deformation. And then after generating the data set, we did this correlation matrix In this chart, the higher value means a strong correlation between two parameters. So from this chart, we can actually say here the delta P. It means the pressure change during the CO2 injection. It actually has the highest correlation score with this UY, means the deformation on y-axis. So it says the pressure change shows a very strong positive correlations to deformation, especially on y direction. And this right chart is the result from principal component analysis. This is a typical tool we use to reduce the dimensionality, especially when we want to make our computation more efficient. So in this chart, we can see the result like offside and pressure change. They contribute very similar to this PC1, means the first principal component. And Y of the reservoir is another parameter and contributes to another different principal component. And other parameters like alpha, which is a belt coefficient of the rock, and deep angle and other parameters, they are all clustered. So from this one, we can, from this analysis, we can, if we want to further analyze different parameters contribution or combination, we can use the result from this analysis. And then as the test data set, it was generated using this software. It's called Bright, and it's a finite element solution software. And in this software, we built the geological model and put all the parameters in the software and do the simulation, then export the final deformation and use it as the testing data set to test our model. And regarding our model, we built two different models. The first one is the artificial neural network. We tune the hyperparameters, for example, the learning speed and how many layers of the hidden layers and activation functions or loss functions on each layer. And then we train this model with our input data and make the prediction. And another model is the machine learning model. We use the gradient boosting regressor as the algorithm and to train our model and validate it. The last step is to predict the model with our testing data set. And here is an example of our results. So the first, it shows how the ground deformation changes with different parameters. So the first row is showing the reservoir depth's influence on the ground deformation. And this left column is showing the ground deformation in X direction, and the right column shows Y direction. So from here we can see when the depth is increasing, actually the ground deformation decreases in both X and Y direction. And when the deep angle is increasing, the ground deformation increases both X and Y direction. So these are examples when we're testing different different parameters influence on the ground deformation results. And this is another results we have for now. The right color means the pressure change at 25 megapascal, and the blue line means the pressure change at 20 megapascal. We test these different models on this different pressure change because as I just mentioned in the correlation matrix, the pressure change has a very strong correlation to the ground deformation on y-axis and also x-axis. So we test different model with different pressure change as the input. And the first row is the result from machine learning model, and the second row is the result from artificial neural network. And we can see both tools can capture the trends very accurately, but when we're comparing the machine learning and artificial neural network, we can see the neural network has some more accurate prediction along both along the different pressure change. But the machine learning, although it can capture the overall the trend, but it has some misfitting around the zero. But this issue doesn't happen on artificial neural network. So here generates our and this is another result we have for comparing the performance. The left side shows the runtime when we're testing different approaches on different sides of the data set. So when the data set is really small, we can just use the analytical solution to run all the calculation, and it's very fast. But when the data size increases, the machine learning and ANN can help us to improve the efficiency. Also, this large data set, this ANN has a very much higher performance than the other two. And in this chart, it shows the accuracy of different models. MAE is the mean absolute error, and when this value is lower, it means the model is more accurate. And R-squared score is the fitness of how the model fit the prediction. And if it's higher, it means the prediction is better. So it's there is an interesting fun, like when we're increasing the size of the training data, the machine learning doesn't actually improve its predictions accuracy with the increasing training data set. It reaches a very high accuracy at this medium size of the data set, but the ANN, it increases the accuracy when we just increases the training data set, the size of the training data set. So here it gives us the conclusion. So first, both machine learning and ANN models can help us to connect subsurface characteristics to the ground deformation accurately instead of using very complicated analytical solution. And then pressure change also plays a very important role to impact the ground deformation in both X and Y direction. And then when the data size scale is ideal, the ANN provides a very good solution. But when the data is limited, maybe we can consider machine learning to provide an efficient way to solve our problem. And the last point is when capturing some detailed information, ANN model always performs better than machine learning model. That's all for my presentation today. Thank you.
Thank you very much. Yeah. Any questions?
So thanks for the talk. So I got a little bit lost at a certain point. But before asking the question, I wanted to understand that I understood it correctly. So you have at the moment you are sort of looking just at a 1D system, right? So you have 1D deformations, and your model there is for the height of this deformation. The analytical model is for the height of the deformation given what happens under the geology under the surface, right? And the amount of the distribution of CO2, I guess, or the pressure that the CO2 exerts underneath, right? And then depending on maybe you have some cracks or holes in the rock strata, then the shape of the hump that you see on the surface is going to be different.
Yes.
Okay. So it sounds a fantastic idea, but my question was whether it is clear. It's not completely clear to me that the system is knowable, meaning that just by looking at the deformation, you can always isolate only one type of subsurface cracks or faults or morphology, let's say, that generates exactly that hump. In other words, knowing what happens subsurface, you can go forward, but if you have a many-to-one let's say relation, then you can't go back, right? So is it clear that there is always, in a sense, you always have enough information to go back to what is underneath the surface with accuracy?
I think if we train the model very
No, but that's not about the model. It's about
but
how the
you mean
different
how to do
parameters
the
clump
inversion?
together to make the thing that you measure.
I think it's feasible, like if we have enough information from ground deformation to the subsurface, and we can train them very like a lot of time and to see if it can capture the patterns.
But the thing is that if, for example, you have two parameters that always clump together, let's say alpha times beta always comes as alpha times beta, you can't go back if you only measure, if the thing you measure is only sensitive to alpha times beta, you can't go back to alpha and beta, right?
Yes,
So-
that's, yeah,
So
yes.
there are many models that when they produce data, right, and then you only look at, for example, the genotype phenotype, right? You only look at some traits, and these traits are only given the combination of this and that in a specific combination. Then you can't go back. You need to make extra measurements. So my question was whether it's clear that you have enough information in the deformation of the surface to go back.
Okay, I think maybe we can animate this effect of the combination of the parameters using the PCA. And if we got this corresponding, then maybe we can say this one fits in this side of the combination, and then the further step will be figure out how these combinations, the parameter combinations influence on each other.
Thank you for the presentation. So based on your results, the 8 and N provide better results than machine learning, right?
Yes.
Could you say that for other applications on other projects and other studies will be the same, or it depends on a specific study that you are using your study?
I think it first depends on how much data you have to train the data.
So if you have a lot of data, it's better to use the neural network.
Yes, I think so.
But it works the same. So it's the methodology, or you can use one or two. You can use the neural network better than the machine learning if you.
Because we want to try different models and see its running speed. Because sometimes when the data set is really large, the training time for the ANN costs a lot. So sometimes machine learning is much faster if you have a very reasonable data set size.
I have a very general question on the system, because you showed at the beginning that the system, it's like there's a water mass below the place where you store the CO2, or where the CO2 was stored. So if you have a high density of CO2 underground and it's in contact with water, will it not just pass, the CO2 will pass to the water, which will acidify? So once the CO2 enters the water system and it enters the water cycle, doesn't it just then leak like through? If the water then, I don't know where this water goes, but once the CO2 is in the water, then the system is not closed. Can it have effect like on the ecosystem because the water underneath is acidified, or can it just, they're trying to store CO2 underground, but if it can flow out the water, is it like a closed system, like a safe system? I don't know.
We only consider
Yeah.
closed system here
Yeah.
and only storing the reservoir and not connecting with the fluid flow.
Yeah,
to
but I mean,
open.
chemically they are, and as it happens with the atmosphere, no? Like CO2 gets in the water and then
If it's dissolute to the water, it's very small portion.
is it a small part? Okay.
I think so.
Yeah, I may add something.
Yeah.
So what the CO2 has a at this pressure and
Okay.
temperatures, the dissolution of CO2 is about 4%, depending on the salinity of the water. These waters at 1-2 kilometers, they are hyper saline. So
Okay.
much more saline than seawater. And therefore the salinity, the dissolution of CO2 becomes smaller
Very
than
good.
1%. And once the water is dissolved, you are right, it's an acidic solution, so you may start dissolving some minerals, but then the processes are because of diffusion and the time scales go to hundreds of years and then going up to millions. All these
Okay.
convective cells that may be driven because of density-driven fingering that start dissolving more fluids. But we have been in other studies, we have done investigation on put this CO2 reach the surface, even if we have a very bad cap rock. So she was showing that we need this low permeable rock that prevents the CO2 from coming back to the surface or groundwater. And these are rocks that have keep hydrocarbon for millions of years, so they are proven that they can trap these gases. And even considering a bad rock with high diffractions, we find that at million-year scale, the CO2 will not really go up more than 100 to 200 meters, and will stay in the subsurface. So leakage is quite unlikely. It could happen. It's more likely to happen if there are abandoned wells. So here in Spain, we don't have a lot of wells because the hydrocarbons are limited. In US, they have hundreds of thousands of wells, and some of them were just abandoned without much taking care of them. But detecting, so for instance, here in Salah, they had one of the observation wells that had leakage, and they could detect and prevent. There are ways of sealing these leaking wells with cements or some gels. There are many ways. There are people looking at methods to seal the wells, the leaking wells. So this would be the main risk, that there is one well that gets damaged, the cement that is sealing it gets damaged and CO2 leak through it, but that they could be fixed and they are monitored to ensure that they are not leaking. So in principle, it's a system that is quite safe. They are highly monitored because we don't want the CO2 to reach the groundwater because it could reduce the groundwater quality and urine. So, and there are ways of remediation.
So it's a water mass which is kind of isolated from the rest of the.
It's quite isolated. They are deep there, and there may be connections. There are some faults that have some flows. Principle, we look at places where we inject the CO2 and it stays there.
Okay, thank you.
Got another question. Is it possible to validate your result with a field survey?
That's our next step to use the data from the ground monitoring and to verify if it's accurate, can accurate match the subsurface condition.
I have a question similar to Marco. So, did you try already the inverse modeling, or maybe this was one of your steps?
It's currently in my work.
Because what I understand right now, you have an analytical solution that, in theory, also gives you very fast results. Maybe not as fast as machine learning for super large data sets, but it's already analytical, but means it's already a very efficient solution. But maybe for the inverse part, the machine learning has the bigger advantage, like the neural network has the bigger advantage. And maybe because to turn a High-King's solution to the inverse may be more complicated than this one. with the machine learning model or with the neural network. And maybe you can plot also, I mean, as he said that you maybe cannot separate A and B, but you make like this kind of like combination matrices, of which are the most likely
Yes,
parameter combination.
that's a good idea.
Okay, so we can end here. Thank you very much.